This video will help you understand how we can come up with ligand field splitting patterns in geometries other than the familiar octahedral or tetrahedral geometries. The first thing that you probably should do is stop this video right now and sketch out a picture of the 5 different d orbitals, because all of the splitting patterns depend on an understanding of how the orbitals are oriented in 3D space. So hit the pause button and do this now. So just as a quick check, remember that the dz squared and the dx squared minus y squared orbitals are directly on the x, y, and z axis. So if there's a squared term, it's on the axis. Okay. But to come up with the d orbital splitting pattern for an octahedral geometry, we can use the following system. So first of all, in step A, if there are no ligands around, there is what we call the no field case. And in that case, the 5 d orbitals all have the same energy. Now we're going to imagine building up an octahedral field as part of a 2-step process. The first is to make a spherical field of ligands that is equivalent to 12 electrons or 6 electron pairs, as we would have in the octahedral field. So imagine taking a globe and smearing peanut butter out uniformly on the inside of that globe, and then putting the 5 different d orbitals inside of it. In this case, all of the 5 orbitals would still have the same energy as each other. That is, they would be degenerate because all of the d orbitals have lobes that would be pointing at one point or another towards some of the electron density. So therefore, the d electrons and the spherical field electrons would all repel each other to some extent, therefore increasing the energy of the d electrons. Now we're going to take those same 12 electrons and focus them at the plus or minus x, y, and z orbitals. When we do this now, the dz squared and the dx squared minus y squared orbitals are now pointing directly at regions where there is high electron density. The dxy, xz, and yz orbitals now have less electron density pointing at them than when they were in the spherical field. Therefore, they will actually go down in energy. Notice that there is what we call a barycenter when we compare figure B and C. That is, the d orbitals in the octahedral field have the same total energy as they did in the spherical field because the size of the field is the same. However, individual orbitals go up or down in energy. So again, we could take the fact that the 3 orbitals are going down in energy the same amount as the 2 orbitals are going up in energy, and deduce that the 3 going down can be multiplied by 0.4 and minus 0.4, that is, and the 2 going up multiplied by 0.6, and the totals then would add up to 0 when we put both of those numbers together. So the barycenter is the 0 energy point in the complex. That's what happens when we have the octahedral field. But what do we do if we have a geometry other than octahedral? Well, basically exactly the same thing. We just have to remember 2 things. Orbitals that point directly at ligands have high energies, and orbitals that are in between ligands have low energies. And so we can use the diagram that is in your workbook to kind of summarize the results for geometries, some of which are familiar and others less so. So all of these diagrams are built so that they have the same barycenter. Okay, then some of them have different numbers of ligands. So step B in the previous slide would be slightly different because we might have an 8 electron or a 10 electron or a 12 electron or a 14 electron field. But either way, the high energy orbitals, the ones pointing directly at ligands, are going to be in the top of this figure, and the ones more in between orbitals are down below. So if we take an unfamiliar geometry like the pentagonal bipyramid showing on the right here, we could probably make a guess and notice that the z orbital or the z axis has been identified here as being the one that is unique, that is perpendicular to the 5 electrons in the pentagonal plane. So we would probably guess that the dz squared orbital would be high in energy because it's perfectly oriented at the 2 ligands that are trans to each other, plus the donut of the dz squared orbital is pointed to some extent at all 5 of the others. Then the dxy and dx squared minus y squared orbitals are equivalent to each other and next in energy, because to some extent or the other, they're going to point at the 5 ligands in the plane. Then the xz and yz are in between orbitals and therefore the lowest energy in those cases. So we can usually make a pretty good guess as to what the rankings of the orbitals are, but we would probably not be able to, deduce the actual energies because that requires some kind of quantum mechanical calculation. So you can assume that you would have this diagram available to you as needed for the unusual geometries, but you should know the patterns for the tetrahedral, the square planar, and the octahedral splitting diagrams.